Hello, everyone, and welcome to today's webinar. My name is Dan Abell, and I'm a research scientist here at Radiusoft, and I'm an expert in modeling spin dynamics and particle accelerators. Spin is a fundamental and not yet fully understood property of particles, such as protons, neutrons, and atomic nuclei. But the origin of spin, how it arises from, from whatever lies inside those particles, now stands as perhaps the most significant unsolved puzzle in nuclear science today. The machines scientists and engineers have built to help solve this puzzle are among the largest and most complex machines ever constructed. Shown here is the Relativistic Heavy Ion Collider, or RHIC, at Brookhaven National Lab on Long Island. The two main rings, here coded in blue and yellow, each have a circumference of about 2.4 miles. The two rings use magnetic fields to guide the counter-rotating beams in the tunnel to interaction points where the rings intersect and the beams collide at the centers of giant detectors. This photograph shows the Phoenix detector opened up for modifications. We hope the next machine currently under design, the Electron-Ion Collider, will enable scientists to fit together more pieces of the puzzle that is spin. Today, I'll demonstrate a simulation, that of crossing a spin resonance, that illustrates one of the most important considerations in designing such machines. Because this webinar will later be posted to Radiusoft's YouTube channel, I'll begin with some background information about spin, what it is, why we care, and about spin resonance in particular. The story is a fascinating one, and I'll provide some references and resources in the final slides. What is spin? How does it arise? And why do we care? I'll give you Michael Faraday's answer to Chancellor of the Exchequer William Gladstone, who, concerning electricity, asked, "What's the use of it?" Michael Faraday replied, "I've no idea, sir, but someday you will tax it." When scientists first began wrestling with the concept of spin, they viewed it as one more piece to fit into that vast intellectual puzzle that is the universe around us. Today, however, spin is a great deal more than that. Nuclear spin is fundamental to the workings of atomic clocks, without which GPS navigation would not work. Nuclear magnetic resonance spectroscopy is now used to help decode protein structures. And very recent work has demonstrated the use of nuclear spin as, of all things, a gyroscope. And the intrinsic spin of protons is central to the technology of magnetic resonance imaging, or MRI, which is today's gold standard for medical imaging. And today we tax it. Recent experiments at RHIC have helped elucidate the internal structure of the proton and how that structure contributes to the proton spin. But even as our understanding has evolved from what it was 40 years ago, there remains some 50% of the proton spin that we cannot account for. The experiments involve colliding a high energy beam of protons into another high energy beam of protons, or in the case of the EIC, electrons. We then search for clues amidst the debris generated when a particle in one beam smashes into a particle in the other beam. Now, for that debris to yield clues about spin, we need to know upfront the relative spin orientations of the two colliding particles. We want a particle-particle collision to look something like this, where the two particles each have a definite and known spin orientation. But we do not know about individual particles in the beams, only about averages over particles in the beams. This means that for an experiment to yield useful clues that help us understand the origin of spin, we want all the particles in one beam to have their spins aligned, and we want all the particles in the other beam to have their spins aligned also. We call such beams with well-aligned spins highly polarized, and we make that quantitative with a metric called polarization. The efficiency of these experiments, the amount of useful data obtained per unit of beam time, increases dramatically with polarization. Moreover, machines such as RIC or the planned EIC require enormous budgets to operate. So we can save time, money, and energy by making the experiments more efficient. Computer simulations of critical aspects of the machine can help lower the risk associated with building the machines for these experiments. As I promised to simulate crossing a spin resonance, let me say what I mean by that. Concerning resonance, nearly all of us at a very young age have climbed onto a swing and had a parent push us. And if mom or dad pushed us at the right frequency, in sync with our swinging, then we experienced, usually with glee, the large amplitude motion that characterizes resonance. Concerning spin resonance, just as a spinning top rotates in a gravitational field, we call it precession. Particle spins precess about magnetic field lines, and they do so at a rate proportional to the magnetic field strength they experience. Moreover, as a particle gains energy in an accelerator, the magnetic fields increase correspondingly, and hence the spin precession increases, the spin precesses at an increasingly higher rate. Because the dominant field seen by particles in a ring is the vertical bending field in the dipoles, we want the spins aligned vertically with that field. Of particular concern then are the quadrupole magnets required for focusing the beam. Particles that undergo vertical excursions in the quadrupoles will see a horizontal field, excuse me, they'll see a horizontal field that will tip the spin forward or backwards away from the vertical. And because that, excuse me, in this last, I'm sorry, I lost my place. On the left here, you see an image of what the spin vector looks like as the particle circulates multiple times around the ring. At the upper right, you see a bird's eye view of the spin motion, of the same motion, but now showing the spin precession over the course of a single turn, starting at about 2 o'clock. From the perspective of the particle rotating about the ring, the spin rotates about the vertical, its vertical, a little under twice. And at the bottom is a similar situation, but one in which the spin precesses slightly faster, completing exactly 2 turns during 1 trip around the ring. The number of such spin rotations is called the spin tune. In this last case, with a spin tune of 2, a spin executing vertical betatron motion can feel just like that younger you on the swing, feeling a tiny tipping force turn by turn at the same moment in its precession, causing it to tip to a large angle well away from the desired direction of polarization. Because that large angle can differ for different particles, this state of affairs can depolarize the beam. This is not good. Worse, though, is that as we accelerate the particles and the spins precess more and more rapidly, they cross many such resonances. There exists, in fact, a whole menagerie of such resonances characterized by the formula near the bottom of this slide. One important question about a resonance is a number we call the resonance strength. Asking how strong is a resonance corresponds to asking who's pushing the swing. Is it Dan or Dwayne "The Rock" Johnson? Oops. The Froissart-Stora formula shown here, makes this quantitative by relating final polarization to initial polarization in terms of the resonance strength, epsilon, and the speed alpha at which one crosses the resonance. The graph here shows what happens to particles crossing such a resonance. They begin below the resonance energy with the vertical spin component exactly 1. So these spins are perfectly vertical. Then as the beam energy and hence the spin tune increases, the particles cross a resonance and the spins end up tipped well away from the vertical. Reading off the initial and final values and inverting the Froissart-Stora formula, one can extract the resonance strength. This is one simple means of extracting resonance strengths from a simulation, and the one we'll use here. There are, of course, many other approaches to calculating resonance strengths. The accelerator tracking code Zgoubi is used at labs throughout the world to model a wide variety of accelerators. Moreover, it has included the ability to model spin since 1992. Despite its well-deserved reputation for being difficult to learn, it remains widely used, a testament, I believe, to the amount of work its author, François Maillot, there in the yellow shirt, has put into developing Zgoubi's capabilities over many years and into writing, and as well into writing very complete documentation. Because the spin of a particle is exquisitely sensitive to the magnetic field it sees, and that field can depend sensitively on the particle's trajectory. Think of a particle crossing a quadrupole field. Zgoubi's ray tracing approach to particle tracking lends itself to the accurate modeling of spin precession in accelerators. By incorporating Zgoubi into our Sireppo framework, Radiusoft has made Zgoubi much easier to use. Here is the machine I'll use for our simulations. It is the Los Alamos Proton Storage Ring, or PSR. I like using this machine for a number of reasons. There's an excellent paper by Dracht analyzing the PSR, which makes this lattice an excellent choice for benchmarking codes. In addition, this is a medium energy machine. The design kinetic energy of 797 MeV means one cannot get away with ultra-relativistic approximations. Also, it's small, which means simulations can run quickly, and that enables one to explore and develop intuition about various accelerator physics phenomena. The PSR comprises 10 cells, each with a 36-degree bend and 2 quadrupoles. There are also 2 sextupoles for chromaticity correction. To simulate a spin resonance in this machine using Zgoubi, we need to make a few modifications to the standard example available in the Zgoubi examples directory on Sireppo. That example already simplifies the machine by not including the injection and extraction lines. I will also track just a few particles so that we can see more clearly what is happening. We also need to lower the energy to somewhat below the energy of the resonance of interest. Scale the magnetic field to that initial lower energy. Insert an RF cavity in order to accelerate the beam. And we have to remember to turn on spin tracking. So on to the demo. So when you go to Sireppo.com, you will see this page, and in the list of supported codes, there are quite a number of them. Down here at the bottom is Zgoubi. And when you first go to Sireppo and go to Zgoubi, you'll just see an examples directory. I've since created this other directory, PSR with spin. So I will go in there and open up the PSR. And here's that lattice. The blue are the bending magnets, the red are the quadrupoles, and the 2 greens up here and down here are the 4 sextipoles in the machine. Now, to get started, I want to make a copy of the regular PSR. I'm going to call it PSR RF because I want to stick an RF cavity in here because we need that for accelerating. Where did my mouse go? There it is. Create a new element. You will learn some French while you are working with Zgoubi. You do not look for a cavity, you look for a cavité. That's what that is. And I want the cavity that gets locked to the scaling. And I need to put in for this particular type of cavity, I need to put in the size of the ring, which is 90.224 meters. And I'll use a harmonic cavity with harmonic number 1 and a peak voltage of 20 kilovolts. And a synchronous phase, I'm just, in this case, I'm just gonna put the beam at the peak voltage. So I want pi over 2, 1.570, and there are more digits, which I'm not going to put in here. I've already got it set up in another tab. The cavity there can then be dragged over. Whoops, what happened there? You can then take this cavity and drag it into the beam there. And the other thing I said we needed to do was lower the energy of this machine. And that's here in the bunch. There's, Zgoubi uses the magnetic rigidity rather than the kinetic energy or the total energy of the machine, of the particles, to describe the energy of these particles. This 4869 and change is the corresponds to protons at a kinetic energy of 797 MeV. That's the energy in the that's the design energy of the PSR. I want to cross a resonance that is about 240 MeV, actually 239, and so I'm going to go about 25 MeV below that and accelerate to 25 MeV above that, so crossing about 50 MeV. So I want to start at around 215 MeV, and so that corresponds to a magnetic rigidity of about 2237 kilogauss centimeters. And that's just a factor of 1,000 from the Tesla meters that most of us are used to. Save those changes. And then I'm going to go back to the lattice, and the other element I want to put into here is not really an element, but it is. That's what we need in the lattice. And it's this scaling element here. And I will call it scale. And we want it to be active. And there are 2 types of magnets in this ring. There are the bending magnets, and there are multiple magnets. Both the quadrupoles and the sextipoles are implemented as multipoles in this example. So I'm going to tell it I want the bending magnets, and I want a scale factor, and that scale factor is going to be the scale, the ratio of the magnetic rigidity we want, which is 2237, to the design magnetic rigidity of the PSR lattice, which is the way all of the magnets in here are already scaled. You enter the fields in terms of the actual strength of the magnetic fields, not in terms of B over B rho, as in many other codes. So that ratio of 2237 to 4869, and I'm not remembering the number at the moment, but it's, 0.45 something or other. And it's important you get that right. You can't just fudge it the way I'm doing it here, which is why I'm going to go to the other tabs and show you the simulations I've already worked with. And so we do that for the bend, and we do that for the multipole. And then we put in the correct scaling, which again, you have to be very precise. Zgoubi will happily tell you that all your particles have been lost after one turn. That has happened to me many times. So you then save the changes, and then you can go to the visualization tab. The other thing in the bunch is I said I wanted to simulate just a few particles. And to do that, I have to tell it, I don't want a random distribution. I want to put in some specific coordinates and save those changes. And then I want to tell it to specific coordinates. So I can tell it, I want 4 particles, and I want particle 1. Remember the resonances are particularly sensitive to vertical betatron motion, with particles seeing those horizontal fields in the quadrupoles. And so what I want to do is launch just a few particles at a few points on the vertical axis. On the vertical axis up above the origin. So I can put in here and say particle 1 has an amplitude of 0.8 millimeters, and I can put in particle 3 and particle 4 and so on, and save those changes. And then in this case, because I set the cavity voltage to that will be a big bug coming in. That's not 2 to the 31. I wanted 20 kilovolts. Okay, we would lose all those particles immediately, instantaneously. So with a energy gain of 20 kilovolts, I want to go across 50 MeV. So I need 5,000 turns to do that. And so in the visualization tab, I can tell it I want 5,000 turns, and I can save those changes, and then I can start the simulation. And after I do that, and the run will complete in a couple of minutes, I will see something like this. This is a simulation where I used 5 this is 1,000 turns. So I must have used, for this simulation, I used a cavity voltage of 50 kilovolts per turn and only 1,000 turns. And now when I want to look at, so here you see that I started at 215 MeV and ended up after 1,000 turns at around 265 MeV. So I'm crossing that resonance that's just below 240 MeV. And I'm going to show you what the vertical component of the spin looks like now as a function of the kinetic energy, which is similar to as a function of the spin tube. And I want to look at all the particles and save those changes And oh, so because this was run at 50 kilovolts per turn, we were sweeping through the resonance very quickly, and the particles do not have much time to get tipped far away from the vertical. And there's one particle up here, the one that was on the origin, is not tipped at all because it doesn't see any of the vertical betatron motion. And the particles that are a little bit up and further up, and then here 1.2 millimeters up from the axis, get tipped varying amounts. And we can plug in values for the P initial, P final, and the rate at which we cross the spin, the rate at which we're crossing the spin resonance, we can get from that earlier curve of the rate of energy increase. And when you do that, you get, say for this, this particular particle here, a value of about 1.2 times 10 to the minus 3. And that is astonishingly close to the actual amplitude of that particle, which is 1.2 millimeters. And that is an astonishing coincidence. I view that as purely a coincidence. Now, in this simulation, I ran the same energy particles. Well, let me be sure I'm not lying. Yes, same particles, but now the RF cavity in this case was set to, well, that says 10 kilovolts, but the synchronous phase is set so that it's half that as the actual energy gain per turn. So this is also, so this is 5 kilovolts per turn, and I'm going across 10,000 turns to cross the same energy. So I'm crossing the energy, crossing the resonance much more slowly. And the final values are different. There's more time for the spins to tip over. And if you, but the energy gain per turn is slower. If you plug these, the values in from this graph into the Froissart-Stora formula and invert it, you get the same values for the resonance strength. A little different because you're trying to pick off numerical values off this data. So again, you get something like 1.2 times 10 to the minus 3 for this particle here. Now, in this last case, I am crossing a different resonance. In this case, I'm crossing a resonance that's about 3.12 GeV, kinetic energy. So this is a much higher energy. And when we go see the visualization, you'll see that apart from the particle that's on the origin, the particles lose, their spins flip almost all the way over. The particles tip almost all the way over. And there's a very nice visualization down here showing on a sphere, on a unit sphere, the location of the spins as the particle is circulating the machine. This is turn by turn. So each one of the dots here shows where the spin is when it gets back to the beginning of the lattice. It looks a bit like there's 4 particles here because you see these four arms standing around like going around like this. It's actually, I'm only showing particle 2, which is this particle here, and it's coming down to a little below the equator, which is what you're seeing here, where these where the spin is ending up. The reason for those four arms that you're seeing is that the fractional tune is around a quarter. So the stroboscopic effect is just, we're seeing the particles at, you know, every quarter around this sphere, and it's not quite a quarter, so it's rotating a little bit as the particle goes down. So the takeaway here is that the resonance strength that you compute here, if we do that, is rather different in this case. And so how we cross these resonances, how we deal with these resonances needs to be different. And that's an important consideration that I'm talking about, this resonance versus the other one that we were looking at. They have to be treated differently, and that's a good place to stop. And I will entertain questions.
All right, thank you very much, Dan. A special shout out, looks like we have Dr. Mayo here with us today. So hello, Dr. Mayo, thank you for coming. I hope you enjoyed the webinar. Our first question that we have for Dan is this one. How would I continue the Zgoubi simulation outside of Sarepta?
Oh, that's a very good question. So there are two things for me to point out. And there are on the Radiosoft YouTube channel, there are a number of webinars that talk more about the Sarepta interface. So I did not do much there to learn how to build the PSR lattice and the Sarepta interface and stuff like that. You can see some of those other webinars. The question here is, how do I continue outside of the Sarepta interface? In this gear icon, I can export this simulation as a zip file. I can download the Python source, and that then contains, after you've gone through the effort of creating the simulation in Sarepta, but when you export these that zip file and look at it, you can see the actual Zgoubi input file that you need, and then you can, if you're already a Zgoubi power user, you can modify that input file and work from the command line. That's definitely one of the nicest features about Sarepta, is that because of the difficulty of working with Zgoubi, it's very nice to be able to create the lattice in Sarepta and then export it and do other things that might not be available in Sarepta with that lattice. And then let me, while I'm here, mention that the other really nice thing you can do is there is a link button here, and you can copy this link, email it to a colleague, and your colleague can drop that link into their web browser and see exactly the same simulation that you've developed here. So that makes it very, very nice for collaboration.
Excellent, thanks, Dan. Our next question in the queue is there an option for Zgoubi to include synchrotron radiation?
Yes. The same place where I turned on the spin tracking. Actually, I'm not sure I showed you, I might have skipped that little detail. In the bunch tab, where you tell it your type of distribution and the energies and all that, there's this tab for the spin and synchrotron radiation laws. So you can turn on spin tracking. You can also turn on the synchrotron radiation. And you can have them both on because you can simulate what happens with electrons, because they're radiating, and how electrons behave in machines is very, very different from how protons behave, and that has everything to do with the synchrotron radiation.
All right, thank you. We have time for one more question before we hit our time limit here. And the question I have queued up next is, let's see. Do you often encounter more than one spin resonance?
I'm sorry, what was that?
Do you often or usually encounter more than one spin resonance?
So, well, first of all, you have this whole menagerie, so you're crossing many, many resonances. And that formula is that the spin tune is an integer, and particularly it's an integer multiple of the periodicity of your ring, plus or minus multiples of the orbital tunes. And so depending on your the orbital tunes and the integer, you can have resonances that are very close together, and you have to deal with what I was showing here was a very, very simple isolated resonance, but you can have resonances that are close enough to interfere with one another, and that's definitely a complication that people have had to work with and deal with.
Awesome. Here we go. I think we have time to squeeze one more in here. This is from Dr. Hofstetter. Can you compute spin resonance strengths for fully coupled lattices, e.g. with XY coupling or optics? And that question is in the chat for the panelists if you want to read it yourself, Dan. I know it's kind of hard to hear me understand it.
That's fine. So the Zgoubi can certainly work with fully coupled lattices. You can insert misalignments. You can have the multipoles rotated. And so one could, the Froissart-Stora formula, I think, is derived free. Oh, never mind. It's definitely derived free for a single resonance. But I don't see why you can't have a fully coupled lattice and work with that.
Awesome. Thanks, Dan. And we're going to squeeze one last question in, and then we really do need to hit our time limit. This is from Frank Schmidt. Is the code benchmarked to other codes like the spin package in PTC or BMAD?
So there's a paper by Etienne Faure from 10-ish years ago. I forget. It's available on the web, and you Google Etienne Faure and Francois Mayo and Zgoubi, and you'll find it. And it's a benchmark that Etienne and Francois did between Zgoubi and PTC. And Etienne's comments about PTC were that its fringe field models were much better than those in PTC. And that aside from the PTC uses the longitudinal coordinate as the independent variable. Zgoubi uses distance along the trajectory as its independent variable. And that's effectively the same as using time as the independent variable. But the agreements between Zgoubi and PTC were very good.
All right, so that is our time for today. So thank you everyone for coming out and hearing our Zgoubi webinar. Thank you to Dr. Dan Abell for presenting this and putting in the work to get it out there for you guys. I hope you enjoy. Please feel free to email us with any questions. Dan, do you want to put the contact slide up so people can see your email?
I need to fill that out, and it'll be on the slides that will be available on the web, and on our YouTube channel. There will be a link to the slides from there.
Yes, we will send everyone who registered a follow-up email with the slide deck and the links to the webinar that they can reference later. And you can also contact us at support@zrepo.com if you have any other questions. We'll make sure that you get in touch with the correct person. So thank you, everyone. Please join us next time, and we'll see you soon.
Great. Bye-bye.
Thank you.